Hey everybody, it's Mr. Carr again. Today we're going to be looking at 5-3 day one. Okay. The goal of today, we're actually doing a little bit of stretch from our identities a bit. We're going to take a little slight break, but also use them sometimes for other things, some of the basic ones. But we're going to do this with solving trigonometric equations. Okay. So we're going to solve trigonometric equations with both our algebra as well as our basic identities. So what does it mean when I talk about solving? So here's one example here. Find all solutions to 5 times the cosine x plus square root of 3. Or sorry, 5 times the cosine of x equals 3 cosine of x plus the square root of 3. Give exact answers in radians. Okay, so we're going to get practice with our radians here. If I treat this just like any other algebra expression, I want to try to isolate x as best as I can. So first thing I'm going to do is going to combine my like terms. So I subtract 3 cosine x to both sides here. Okay, so that's going to give me, I'll rewrite over here a bit. That'll be 2 times the cosine of x is equal to the square root of 3. Again, my goal is to isolate that x right there, so I'm going to divide both sides by 2. So the cosine of x is equal to the square root of 3 over 2. So here's what we're looking at in this case. Instead of doing it as like the inverse cosine, so I could solve for x here, instead, I need to think about it in terms of my unit circle or just modeling with my special right triangles. So when is cosine a positive value here? It happens in the first and fourth quadrants. Okay, so I'm going to model this triangle in both those quadrants. And again, you can use a unit circle here if that's something that's helpful for you. But I'm going to go through and just do this with my reference triangles here. So this is cosine, so it's adjacent over hypotenuse. So it's going to look something like this. Okay, here's the first version where it's going to be the square root of 3 and 2 right here. But since I can do it in the fourth quadrant as well, I can basically draw a reflection of that triangle, pretty close, and make it look like that. That's also going to be a positive root 3 over 2 for the cosine. So the question is, which angles are these? Well, if you recognize it, this is going to be a 30, 60, 90 triangle in both directions. So this first one here, what I get is going to be x is equal to pi over 6 for that first one. Okay, that's this one right here. The other one is going all the way around to that spot for that reference point. So it's pi over 6 away from 2 pi. So the other equation or the other solution here is 11 pi over 6 because it's not quite 12 pi over 6. It's 1 pi over 6 short. So the one thing about this is it's asking about all solutions. All solutions is the fact that because of the periodic nature of this value is going to repeat all the way around one more time. And then it goes again on another one and another one. If we keep going around and around, we're still going to get solutions to x here. Okay. The idea is that I could take pi over 6 and plug it in here and here, and I get to a true statement. But there's other values that are coterminal to that. So that's what I need to do there. So x is actually going to be equal to pi over 6 plus the coterminal idea, which is 2 pi times n. And the same thing can happen here. I'm going to write that one out as well. So these are all of my solutions, 11 pi over 6 plus 2 pi over n, or 2 pi times n, as long as n is any integer. Okay, so n is any integer. This is going to represent all the possibilities here. Okay, so again, it's this one and every coterminal one around it. That's what I'm saying with this statement. Same thing here. It's this one and every coterminal angle to that one as well. Okay, so same thing on the next one. I want to find all the solutions to this. So we're going to do the same kind of process. Okay, so same thing. I'm going to try to get x by itself as best I can. So we'll start with adding 4 to both sides. I'll rewrite it over here. So 3 times the tangent squared x is equal to negative 3 plus 4, which is 1. Divide both sides by 3, so I get tangent squared x is equal to 1/3. And then, just because like this is exactly like saying or tangent x squared, I could undo the squaring by square rooting it. But just like with before, I got to do the plus or minus version. So I got the tangent of x is equal to a plus or minus. If I do this as the square root of 1, it's 1 over the square root of 3. I could rationalize this, but I don't need to because I'm just trying to get to my answers here. So I'm going to model when is tangent going to look like this, where it's 1 over root 3. And it's a plus or minus. So I get 4 possibilities here. because the positive tangents, remember, it's going to be in the first quadrant. So it's actually going to be right here like this, because it's going to be opposite over adjacent. So it's 1 and √3. And then this is the other positive tangent, okay? Oh, no, sorry, no, it's not. That's not the positive one. It's all students take calculus. So this is my positive tangent over here, okay? So that's 1 and √3 there. But additionally, because the negative tangents are going to come from here, okay? And here. Yeah, close enough. All right. So same thing as before. I need to figure out what are these angles? What are the radians of each of these? Okay. Once again, I have my 30, 60, 90 triangle, or in this case, what I could say is that is pi over 6. Okay. So what I get is pi over 6 here. So x will equal to pi over 6. This one is going to be pi over 6 short of pi. So I'm going to say that's x equals to 5 pi over 6. And I could keep going with all 4 of these, because this one right here is going to be one more than that. That's going to be 7 pi over 6. Okay. So I'm going to write that down, 7 pi over 6. And then the last one here is 11 pi over 6. But if I want to describe all the solutions, I don't need to do this as 4 things with all the different coterminals, because technically, if this is one solution here, this is a difference of pi, and then it's a difference of pi again. So this right here is following a pattern of pi every time. So my first one is going to be x equals pi over 6 plus pi times n, where n is any integer. Same thing with 5 pi over 6. So 5 pi over 6 is my first solution, and then every one after that is a difference of pi. So we're going in these half circles, basically. So I could say, and x equals 5 pi over 6 plus, I have space here, scoot that back a little bit, 5 pi over 6 plus pi times n, where n is any integer. Okay, so again, we don't have to do the full coterminal. I mean, technically that would be correct. If I wrote out all four angles here like this, and I just did it as 2 pi around, but it's just extra writing that I don't need to do because I represent the same solutions with these. Okay, we don't have to go as much then with that writing. All right, so find all solutions of 2 sine of x cosine of x equals the square root of 3 times the sine of x, but only on the interval of 0 to 2 pi. The difference between this problem and the previous ones is I didn't put any kind of limits on it. There's no restriction on where my answer should be. So in this case, it says all solutions. This is all solutions, but only on the interval of 0 to 2 pi. So I'm just going to go through the same process that I would normally do. I'm going to try to isolate as best I can. In this scenario, we're going to end up using, we're going to use some factoring when we go through this. So for example, I don't want to put sine of x here and sine of x here. I want to bring them together on the same side. So I'm going to subtract the √3 sine of x. So that'll look like this: 2 sine of x cosine of x minus the square root of 3 times the sine of x is going to equal to 0. Since I have sine of x in both of these terms here, I can factor that out. So the sine of x is going to be multiplied by 2 cosine x minus the square root of 3 equal to 0. Just like in algebra days, we can do our zero product property. If this times this equals 0, then either sine of x equals 0 or 2 times the cosine of x minus the square root of 3 equals 0. Okay, I'm going to ignore sine of x for now. Let's focus on this one. We're going to solve this for x. So I'm going to add √3 to both sides. 2 times the cosine of x is equal to the square root of 3. Divide both sides by 2 so that the cosine of x is equal to the √3 over 2. So if I model these out again with their triangle, or yeah, basically the triangles, but in this case, the quadrantal angle, when is sine of x equal to 0 on the interval 0 to 2 pi? Okay, and when does the cosine of x equal to √3 over 2? Okay, so we got sine of x equal to 0. So if you remember your quadrantal angles, that's going to happen at 2 spots. It's going to happen here and here. Okay, that is 1, 0 and -1, 0. The sine is the second values in both cases. So on this specific interval, x is going to equal to 0. Okay, not 2 pi is going to equal 0. And it's also going to equal to pi. Those are the two possibilities there. For cosine of x, since it's positive, it's going to be here and here, these first and fourth quadrants. So I'm going to model this. It's going to be adjacent over hypotenuse. So it looks like this. It's going to be here's one triangle, here's the other triangle. Okay, so that's √3, that's 2, and that's 2 there. Just like our earlier examples, these are both going to be in reference angles of pi/6. Okay, so that's the angles right here that it makes to the x-axis. I'm running very messy there. I'm sorry about that. Okay, it's also getting a little tight in my drawings there. But the idea is that pi/6 is my reference angle. So x is equal to a pi/6 and 11 pi/6. So it's the same thing that we saw earlier. Okay, so again, we don't need to represent all the values because we just want to focus on the ones on this interval. Okay, and that's how I can use my factoring to solve for that one. Again, we're going to kind of use some basic identities. That's going to be the focus of the next video, but we're looking at our algebra, our factoring skills, other things like that in order to model our different sines and cosines to solve for them, for these values of x. All right, that's it for today. Take care, everyone.